Okay, I want to thank the organizers of this wonderful program for invitation. Also, I paid them in strange ways, since what I will be talking about is not P and it's not E. It's only the last P problem. There will be nothing periodic or ergodic there. But I was told that it's okay.
Well, as Grisha Razanjuk told us, you will be talking about periodic problems with period equal to infinity.
Okay. So the thing about I will be talking about is humongous, and there is a lot of work done. I will only be talking about small facet of this. I will give you a little bit of idea of what's going on, but in general, but I will touch upon one part of it only. And the mystery is still there to a large extent. So what I will be talking about is nodal patterns of eigenfunctions, let's say of Dirichlet-Laplacian or maybe Schrödinger operator. I will mention what are interesting properties of nodal sets and partitions. I will formulate Courant theorem for nodal count, and then more recent stuff coming originally from Bernard Helfer, who was here the first half of the program, and Thomas Hoffmann-Ostenhoff. And then I will present the main result that I want. So first of all, about nodal patterns. They are incorrectly called Chladni figures. According to Arnold's principle, any name assigned to anything in science is wrong name. So this is just incarnation. Actually, they were known to Leonardo da Vinci, to Galileo Galilei, and Robert Hooke 110 years before Ernst Chladni was presenting those experiments to the Royal Society. Unfortunately, I cannot help saying this, that I don't know about all of you, but I discovered that I knew almost nothing about Robert Hooke, except Hooke's law and his feud with Newton. But he was amazing scientist. Most of the stuff that he did was forgotten quickly and rediscovered 100 years later. But why I recall this, since I saw this book on the shelf in the library of Newton Institute. It's a wonderful book that explains how great scientist Hooke was and how much he did. For instance, I didn't know that, everyone knows that Christopher Wren rebuilt London after the Great Fire, but I didn't know that Robert Hooke also rebuilt London after Great Fire. Essentially, he practically contributed even more, not only building half of the buildings, but also doing the whole survey, land survey before that. And so you will, if you read this book, you will discover that it's he was amazing scientist of huge caliber, and mostly it is forgotten, and unfortunately not without involvement of Newton, as far as I know. For instance, we don't have a single portrait of Hooke, which apparently was due to Newton. They both were great scientists, but not the easiest people to deal with. So, what is this? You probably all have seen machines like that. These are standard devices that are shown in physics and sometimes mathematics classes, where you vibrate a membrane with certain frequency, and you put something like, it could be, Hooke used flour, you can use flour, you can use sand or something else, and whenever it oscillates with certain frequency, with eigenfrequency, then it forms a pattern. A pattern is the following, that the sand congregates where membrane doesn't oscillate. So this is what is called nodal line of eigenfunction, where eigenfunction is 0, so there is no oscillation, so sand moves away from oscillating parts to those. And Hooke, for instance, was showing in a shallow glass jar with flour. He showed how he could produce different sounds from this jar, and he showed the different sounds led to different patterns. So this, you see, this has been noticed several hundred years ago, but surprisingly, it is such a difficult thing to study that even now a lot of stuff is not known. So these are some examples of nodal patterns for a square, for violin, and this is what is called Bunimovich Bunimovich stadium. Actually, those things, like for violins, they used those nodal patterns are used practically when people produce guitars, violins, etc. So
These
this
are
is
plates for actual
what?
solutions for actual plates, thick plates, right? I mean thin plates, but these weren't the Helmholtz solutions of the Helmholtz equation.
Oh, yeah, I will be talking about this. Their solution essentially of not Helmholtz but eigenfunctions of Laplacian, essentially. So it's not Helmholtz. It's eigenvalue problem for Laplacian. It might not be pure Laplacian if you have different thickness, etc. McLaughlin and others.
This one. You're talking about the second order Laplacian. I mean,
Yeah, I will show you. I will show you what will be the operator, but so far pictures. You can imagine Laplace operator in a bounded domain with Dirichlet boundary conditions.
I guess what they meant was that for the actual thin elastic plates, the equations are of the fourth order rather than of the second, right? Or Laplacian squared, you could
Yes,
have
yes.
but that's not
But-
what you consider.
You're right, that you can look at, by the way, those patterns, if you look closely, some of you might recognize, but it's not for Dirichlet Laplacian. I will be talking only about eigen-nodal patterns of Dirichlet Laplacian. For instance, Neumann Laplacian is much more difficult and little is known. This is another example of practically used nodal patterns when people manufacture guitars. And those things are currently studied in mathematical physics. By the way, this is the high day for studies of those nodal patterns. For a long time, there was no big movement, but nowadays people study it all over. Certainly mathematical physics, for instance, studying quantum chaos. In number theory, people are interested in nodal patterns, for instance, for mass forms. Even in medical imaging, it arises, surprisingly, but it is true. We had to work on some still unresolved issues about nodal lines in trying to decide for some new methods of medical imaging where to put the detectors. What are the questions you might ask? Local structure of those nodal sets. Nodal set, again, is a set of zeros. I will have precise definitions later, but set of zeros of an eigenfunction of Dirichlet Laplacian. First of all, local structure. This is not a very hard thing. It's well known that those, for instance, let's think of 2D case for simplicity. Those nodal lines are smooth unless they collide, and when they collide, they have to form equal angles, like zeros of harmonic function. This is an easy part. It's written everywhere, and it's not hard to establish. But if you look at something harder, like imagine, I don't want to spend much time. I could talk for 2 hours just about that. But if you, for instance, know in many areas in number theory and in imaging, the question arises, you have a set which is simultaneously nodal to many eigenfunctions, not to one, to many. And for instance, recent work by Bourgain and Rudnick shows that if you they consider this issue on the two-dimensional torus. I think it's not necessarily two-dimensional, but let's say two-dimensional torus, and they found that if you have a curve on which infinitely many eigenfunctions of the Beltrami Laplace operator vanish simultaneously, this should be a straight line. It's a rational line going around periodic geodesy on the curve. So there is no curvature. And what we need in medical imaging in more complicated situations than Bourgain and Rudnick considered on torus, it's in the whole space. We also we have issues that lead to the study of joint nodal sets of not just infinitely many eigenfunctions, but let's say you have Laplacian in the whole space, and you consider its generalized eigenfunctions, not in L2, there are no L2 eigenfunctions in the whole space, and you look and you assume that there is a set where you have a vanishing eigenfunction for almost any lambda. And then the claim is that it should also have zero curvature, and it's important for medical imaging, but it happens to be extremely hard. And again, this is not what I want to concentrate on. This thing about curvature, I could spend several lectures just discussing this. Another issue is how large is the nodal set. So, for instance, St. Yao conjectured that if you are in dimension n, and if you take n minus 1 dimensional Hausdorff measure, n sub lambda will be the zero set, the nodal set of eigenfunction corresponding to eigenvalue lambda. Very simple examples give you an idea that that's what you expect when lambda grows. And we are very far from proving this. In analytic case, it was proven by Pfefferman and Donnelly. In smooth case, bunch of great people are still working on this, and we are not there yet.
Peter, do you mean the number of nodal
No. It's if in n-dimensional, if you have n-dimensional domain, zeros of eigenfunction for n minus 1 dimensional object. So you measure Hausdorff n minus 1 dimensional measure, since it's not discrete, so you cannot count. So this is still there. And here in the red is what I will be talking about. How many nodal domains does the nth eigenfunction have? And domains I will have in a second exact definitions, but those nodal sets split the domain into connected components. Complement to the nodal set has several connected components. These are components where eigenfunction is either positive or negative. How many of those domains do you expect to have? And you will see some results by Courant and many other people worked on this. So main result I want to present is in this area. There are other things that people do, for instance, inverse problems. Quite some time ago, Hald and McLaughlin, they studied inverse problem if you have whether can you recover mechanical parameters of the membrane from if you know nodal patterns, which you can observe. And another application to inverse problems was due to Smilansky and his co-authors. They looked at the following issue. We all know that there are isospectral domains. So the spectrum itself doesn't determine the domain completely. Their idea was that maybe if you add to the spectrum, if you add the nodal counts for each n, you know how many nodal domains eigenfunction has. They thought that maybe it will resolve isospectrality. Sometimes it does, but there are counterexamples. There are domains that either spectral and either nodal.
So actual domains, not quantum graphs, but actual domains.
Yes, counterexamples, there are counterexamples on graphs. First, they were found on graphs, and then on domains. And now let's get precise. In one dimension, we know this Sturm oscillation theorem that says that if you have this Schrödinger operator on a segment with Dirichlet conditions, then if you look at you arrange eigenvalues in increasing order and look at the eigenfunctions, then the nth eigenfunction change the sign exactly n minus 1 times inside of the segment. So for instance, this is the possible graph of a second eigenfunction. So it actually vanishes once inside and also twice the boundary. And there are two nodal domains. So we exactly know that number of nodal domains is exactly equal to the location of eigenfunction in the spectrum. The third eigenfunction will have 3 nodal domains. The first eigenfunction is always preserving sign. It has only one nodal domain, which is the same, which is also true in higher dimensions. So now what happens in higher dimensions? So let's consider the Schrödinger. You can think the potential doesn't play much role here. You can think that we have Laplacian with Dirichlet condition in a nice bounded domain with sufficiently smooth boundary. It will be all overkill, but it's better not to get into hairy and gory details. So now we label the eigenvalues in increasing order, and it will be convenient for me to mention the domain. So lambda 1 of omega means the first eigenvalue for this operator in the domain omega, since we will be changing domains. So that's why this notation is convenient for me, and corresponding eigenfunctions. Now, nodal set, as you probably already realized, is a set of zeros of nth eigenfunction. Now, if you throw away the set of zeros, you will have those pieces where the eigenfunction preserves the sign. By the way, we are talking about real potential, so eigenfunctions are real. For instance, if you consider magnetic Laplacian, you don't know what nodal set is, since eigenfunctions will be complex. So if you throw away the zero set, it splits the domain into several components that we saw in the pictures. And now we count the number of connected components. I call nu sub n the number of nodal domains for the nth eigenfunction. Now, Kuncment proved long time ago the following theorem. It's a beautiful theorem. It's very easy to prove that number of nodal domains cannot exceed the location in the spectrum. And this is very, it's proved by contradiction very easily. If you have more nodal domains than location in the spectrum, then you can easily create test n plus 1 test functions that form subspace on which the Rayleigh quotient will be below this eigenvalue. You will prove that the number is n plus 1, not n. So it's very easy to do. It's beautiful theorem. Now, Courant sharp eigenfunctions are those when you have this one-dimensional effect, when the number is exactly equal to the number location in the spectrum. Now, one might wonder, maybe Courant was not smart enough to prove that they're equal. Maybe they're also equal. But in 1D it's true. Let's look. First of all, the first eigenvalue is always Courant sharp, since it always preserves the sign, and therefore it has one nodal domain. The second eigenfunction should be orthogonal to the first. It should change sign, and the consideration of Courant theorem shows that it cannot have more than two nodal domains. So they're always Courant sharp, but it might be it. In fact, the Courant estimate, well, it was shown many years, probably 30 something, more than 30 years later by Pleyel, that in fact there is stronger inequalities. The number of nodal domains not only that cannot exceed n, it cannot exceed n with a factor less than 1. And this is for large n. So this shows that if you do have any current sharp eigenfunctions, and you always do have at least two, first and second, but you have only finitely many. Others, if you go far, there will be no current sharp eigenfunctions. Everywhere the nodal count will fall below the location in the spectrum.
What is J? What is J?
J?
Yes.
Oh, it is the first non-zero zero of a Bessel functions. It's interesting that very recently this constant was improved, but improved by laughably tiny number. But it took work of people like Bourgain and Polterovich. So even tiniest improvement in Pleyel estimate requires work of great mathematicians. By the way, on previous slides you notice that there are at least 3 Fields Prize winners involved in this study and many people of the same level. Now, as I said, the corollary is that for higher dimensions there are only finitely many current sharp eigenfunctions. And we denote this difference by, we call it nodal deficiency. Mu n is how much behind the nodal count falls in comparison with the location in the spectrum. And so what can you say about nodal deficiency? Unfortunately, things can go really bad. A student of Courant constructed in his PhD thesis eigenfunctions that have, you can produce arbitrarily large n just with 2 nodal domains. So this is an example where if you go through this maze, you will see that there are only 2 connected components here. And so you can have functions arbitrarily high in the spectrum which have just 2 nodal domains. So now the question is, what's happening? Not that we know completely, but at least there is something that we can say. For instance, is this nodal deficiency something random jumping number? For example, if you look at the square, you will see that sometimes nodal, in this case, nodal deficiency is n minus 2 with arbitrarily large n. In other cases, it might be 0 or close to 0. So what is it? It's some, I just saw a recent paper in Annals of Physics about those things, and I forgot what the word they used, but at least the exact word I forgot, but at least the meaning was that we have no clue what those nodal deficiencies are. There is no regular behavior. So there are some embarrassingly simple questions that we don't know answer. For instance, the Stern's example shows that arbitrarily far in the spectrum you can find small nodal counts. But the idea is that probably if you take lim sup of normal, number of nodal domains, it should be infinity. In other words, it's expected that you cannot have an example where all eigenfunctions have no more than 7 nodal domains. The lim sup is infinity. Well, we don't know this. It's conjectured by Thomas Hofmann-Estenhoff. It's not proven even for 2D Dirichlet Laplacian in smooth domains. So we don't, and big, very strong people worked on this, like Nadirashvili and others. And we still don't know the answer. Now, things started changing several years ago when Helfer and Hofmann-Estenhoff looked at the problem from different perspective. Rather than looking through the equation itself, they started looking at partitions. They said, okay, we have let us have a partition of domain, and we try to figure out, can it be nodal partition for some eigenfunction? I have my domain, I have my operator, Laplacian or maybe Schrödinger, and I have partition. Will it be a nodal partition for some eigenfunction of this Laplace? Now, it seems to be completely, how would I say this, unlikely that you can do this, since the space of partitions is infinitely dimensional. And there is discrete set of eigenfunctions. So it looks like this is completely unwieldy. However, it happens to be not true. So their question was, you have this partition, and what do you need to know to claim that it is nodal partition of some eigenfunction? First of all, there are some necessary conditions, and these are local structures. They should be smooth pieces. Let's think of 2D case. It's not easier than higher dimension. In principle, everything I say works for compact Riemannian manifolds with boundary or without boundary for a Laplace-Beltrami operator, but you can think of 2D Laplacian in nice domain. The local structure should be correct. You should have smooth curves, and when they intersect, they should split the angle into equal portions. So for instance, if two of them intersect, they are orthogonal. And if one of them hits the boundary, it should hit orthogonal. So this is what is mandatory. There is another thing which is kind of very interesting, but I will not dwell on it. That this partition must be bipartite, which means the following: that it should be possible to color your domains in two colors without contradictions. And the reason is very simple. If you color in black the domains where the function is positive and white when it's negative, it's clear that you cannot have the same color on two sides. Since if you do, what you will have, imagine that you have white here and white here, then along this curve, your eigenfunction not only vanishes, but its gradient vanishes. And this is Cauchy problem for second order elliptic equation. It has unique solution, so you cannot have this. So the sign should change, and therefore it should be bipartite. In particular, this picture is impossible. You cannot have this nodal pattern. So this thing you have to impose, otherwise there is no chance. Now, an interesting thing is that this partition must be what is called equipartition, meaning the following. Look, let's take, so we have, this is zero set of nth eigenfunction of the operator in the whole domain. Now, if you restrict it to one of those subdomains, it still satisfies eigenvalue problem, and it still has Dirichlet conditions. Since on the boundary it had Dirichlet conditions, and here it vanishes. Therefore, on each of subdomains, you have eigenfunction which doesn't change sign, which means that it's the first eigenfunction. So therefore, you conclude the following, that if you take the first eigenvalue for each of those subdomains, they are all equal, and they're equal to the nth eigenvalues that you study. So equipartition will be partition such that lambda 1, the ground state energies for each of the pieces, are the same. You don't impose that they're equal to lambda n, since you don't know what lambda n is. You are not sure it's a partition corresponding to eigenfunction, but they should be equal. Now, so these are necessary conditions. Then what they considered was the following smart thing. They, let's say P is partition, and you have this enormous space of partitions. And we can introduce the following functional. Lambda of partition is the maximum ground state eigenvalue among all pieces.
Among all? Say it again, please.
It's maximum of lambda 1 in each of the pieces. Since we don't require that it's equipartition, they're not necessarily equal. You take maximum. And then they did the following. They considered the minimum of this functional over all partitions where you fix the number of pieces. Number of pieces fixed. You have on this unwieldy set this functional, and they took it minimum. First of all, who knows that the minimum exists? It's a really hard thing to do, but they proved that it exists. Moreover, they proved that minima points of this functional, so those partitions that minimize this functional, if they're bipartite, they are exactly nodal partitions for all current sharp eigenfunctions. So every minimum point, it could be either bipartite or not. If it's not, you throw it away. Also, there is an interesting interpretation with magnetic operators of those. But we throw them away, and we only keep minima points which are bipartite. The claim is that they are exactly all nodal partitions of all current sharp eigenfunctions. And that's absolutely beautiful result and really technically hard to prove. Existence of the minimum is something really difficult. And it's a wonderful result, but why? We know that there are only finitely many current sharp eigenfunctions. Most of them are not current sharp, so what happens with those partitions? Where did they go? And why do we get only current sharp ones? And the answer was given first, and as nowadays often happens, you discover something on discrete graph or quantum graph, and then you try to push it, to bootstrap to the adult situation. So it was done first on quantum graphs, which was also non-trivial thing. And then I'm approaching the result that I wanted to present. First of all, I will be talking about generic partitions. So what does it mean generic? For instance, if you are on Riemannian manifold, you can vary the metric. If you are in the domain, you can change the boundary. So what is the generic situation with respect to variations of those parameters? And it's very well known since 40 years ago, due to work by Karen Uhlenbeck, which also followed the work, more limited work by Albert. She proved that generically the following things happen. First of all eigenvalues are simple. Secondly, zero set of an eigenfunction doesn't contain its critical points, meaning that, I should have listed them in, the zero set of an eigenfunction doesn't contain critical points, which means that, first of all, those curves don't intersect. Every intersection can be resolved by small perturbation. And by the way, if you recall this Stern's example, you can see that it is just square grid, little bit perturbed. So we resolve all intersections. So there are no intersections, and moreover, the gradient of the eigenfunction never vanishes in those curves. In particular, they are very smooth curves. Then she also proved that if you take the normal derivative of eigenfunction at the boundary, it has only simple zeros, no zeros of higher order than 1. I will not discuss this. So here is this picture that shows what happens. You have this very non-generic thing, grid, you perturb it, and this is what happens. This is what happens. So what we'll do as a result that I will present holds for generic partitions. So let's look at the billiard case. As I said, it was done first on graphs. And here is our theorem. That if you take only generic equipartitions, so now we consider only equipartitions, partitions where lambda 1 is the same in all pieces. Lambda 1 of each piece is the same. And generic, meaning that you don't have, or everything is smooth, there are no collision of nodal lines and so on. And you look only at bipartite point. Now, what Helfer and Hoffman-Ossenhoff and Terracini did, they looked at points of minima, and we look at critical points. They couldn't look at critical points. Why? Since their functional was non-smooth. Remember maximum of several smooth things. It was not smooth. We restricted to equipartitions where everything becomes smooth, and we look at all critical points. And now the answer is that if you look only at generic equipartitions and look at critical points of that functional lambda, then all bipartite critical points correspond to nodal partitions of all eigenfunctions. So if you look only at points of minima, you only find current sharp eigenfunctions, which is only finitely many. If you look at critical points, you exactly find all nodal partitions of all eigenfunctions. Moreover, the most interesting thing is that the Morse index of it, so you found critical point in the space of partitions. It's bipartite. You know that it is partition of eigenfunction, certain eigenfunction. Now, critical points have Morse index. So, which means that you take Hessian of the functional at this point, and you look at number of negative squares. You are in infinite dimensional space, so in principle, Morse index could be infinite. It doesn't happen to be infinite here. Actually, the statement is that the Morse index of this critical point is exactly the nodal deficiency that this eigenfunction has. So this ridiculous nodal deficiency that didn't show any law obedience, it's actually not arbitrarily thing. It has underlying structure. It's Morse index. So all nodal deficiencies are exactly Morse indices of all critical points of such under those conditions of genericity and equipartition.
Peter, I know who's PK, but who's GB?
Oh, sorry,
Great Britain and US.
yeah, I'm sorry, I was cutting and pasting from previous versions, and so I erased the names. It's Gregory Birkolaiko from Texas A&M, that's me, and this Uzi Smilansky from Weizmann Institute and Cardiff.
And what is in the billiard case?
Oh, so billiard case meaning, I mentioned the first, this kind of result was obtained for quantum graphs. And now we are doing this on the domain, so I call it billiard.
And what are restrictions on the domain?
No restrictions, except that it should be generic.
But you need.
Oh, you need some smoothness. Not that much, but we impose all smoothness that you might want, since we don't want to get into those details.
But it also works for Riemann surface
Yes,
without
Yes.
boundary and so on.
without boundaries, and you vary metric, Riemannian metric. And it's very general thing. So we have this, that's, in my view, the most beautiful part, that the nodal deficiency is actually not arbitrary junk that behaves without any laws and order. It's actually Morse index of all critical points under those conditions. Now, if you are at a minimal point, it explains why they found only Courant sharp eigenfunction, since at the minimal point, Morse index is 0. There is no directions where you go further down. And therefore, what they found, they should have found. They found only Courant sharp eigenfunctions. So this is the main result I wanted to present.
Sorry, but I think I'm missing something there on this minimal points. I think you quoted that theory which said that for any n right number of partitions, you minimize that thing, and they prove the minimum exists, and then it's exactly Courant sharp.
It
right?
might not be bipartite.
Okay.
You see, you find minimum, you have to check whether it's bipartite. If it's not, it cannot be nodal set of eigenfunctions. That's a very good question, thank you for asking that. But so you're right, that they show the minimum exists for any number of parts, but the thing is that it's rarely bipartite. It's rarely bipartite. But our thing shows that for all locations in the spectrum, you do have critical points, and their Morse indices are exactly the nodal deficiencies.
Sorry, by Morse index you mean Morse index of the thing as a critical point, not Morse index of the eigenfunction.
No, it's more, you have functional, I will tell you a little bit about the scheme of proof, but you have this functional lambda of partition. First of all, partitions we need to make into something manageable, some infinite dimensional manifold, and this is smooth functional, it has critical point, and then this functional you look at Hessian, this functional you look at all directions on which subspace it's negative definite, and that's a Morse index, number of negative squares in Hessian. So this is the main result that I wanted to present, and if there are no more questions about formulation, I will give you some steps of the proof. So how it is done? First of all, one of the main things throughout the whole proof is a relay Adamar domain perturbation formulas. That those formulas, these are wonderful formulas that tell you the following: you take domain and then you perturb its boundary. What happens with eigenvalues of Dirichlet Laplacian? How it changes? What is so if you have, like, imagine that this is one of our nodal domains, and I want to perturb it. So the natural way to perturb it is in normal directions. So if you pick unit normal vector field, and then you take a function f of x on this boundary, and correspondingly it tells you how far you go in this direction, and then you put small parameter t here. And so you get domain depending on t, and Adamar formulas, they tell you what is the derivative of eigenvalue when t equals 0, and it is minus, it doesn't have to be the first eigenvalue. And here you have eigenfunction, the normal derivative squared. So this is a crucial formula, since you have to differentiate with respect to partitions. And also, it allows you to do the following, that you can parameterize the space of generic partitions by those functions, at least small piece of the space. So on each component, like this is one nodal component, there is somewhere another, on each of them you have appropriate space of functions f, some Sobolev space, that parameterizes your perturbations at least nearby. You don't want to go very far, you will have conflicts, but locally you have local structure of a Hilbert manifold.
Just a second. So what is f of x again?
What?
F of x in this problem.
F of x is that tells you the profile along the boundary, how far you go in each direction, and psi is an eigenfunction here.
Right.
So you take the normal derivative. The eigenfunction vanishes here, but its normal derivative doesn't. So you take normal derivative of this eigenfunction on the boundary, you square it, you multiply this profile function, and integrate over the boundary. And this gives
Okay,
you,
yeah, I got it. So X is along the boundary.
yes, it's around the boundary.
Okay.
So we have, locally we have the structure, but manifold structure is always local. So essentially what it does, it shows that you have the structure of infinite dimensional Hilbert manifold, smooth manifold. Now, so the space of generic equidistributions can be made space using this can be made the space of Hilbert manifold. And moreover, this functional lambda, it's easy to prove that it's smooth function on this manifold. If we didn't require equidistributions, then the functional lambda wouldn't be smooth. Since you will have lambda 1 different in different domains, you take maximum, which makes the functional non-smooth. However, the result holds even in that case. There is a way to understand what does it mean that Morse index, what is the Morse index of such non-smooth functional, and without restricting to equidistributions, the result still holds. You just need to understand in what sense you have Morse index. Since Morse index you can define without taking hashing, without you can define it as follows: that you look at subspaces where the functional decays, and how big subspace you can have. So that, and this doesn't require smoothness. So in principle, dropping equidistributions, we have this for lambda, which is non-smooth. Then the thing is that it looks like there is a big disconnect here. First of all, our space knows partitions. In particular, on connected components of the space, partitions have the same number of nodal domains. In order to change the number of nodal domains, they have to collide, and we throw away those points. So we have a bunch of disconnected sets of partitions, each of which is smooth manifold. And what does it know? It knows about partitions. In particular, it knows how many there are. If you, in this space of partitions, if you take partition with 5 pieces and you deform it, you still have 5 pieces. So this space knows about the number of nodal domains, but it has no clue about eigenfunction. We have to compare number of nodal domains with location in the spectrum. But who does have knowledge about eigenfunctions? This is, we know well, variational principle. Relay ratio, or you don't need to take a ratio if you restrict it to the sphere. We know that critical points there are exactly eigenfunctions, and you know everything about this. So now we have to connect 2 foreign objects. One is the set of partitions, which is something completely unwieldy, and another functions on our domain. And this is done in several steps. You can realize those functional spaces that related to relay ratio and variation principle as vector bundles over smooth vector bundles over this thing. And then essentially what you will have functional down here on partitions, and another functional on the bigger space on the vector bundle. And the one on the vector bundle will know location in the spectrum. And the one down below doesn't know, but it knows the number of domains. And you need to relate. So essentially, think is that you have like a direct product. Since it's locally trivial vector bundle, you have a functional, and you know, and there is this cross section. This is my E, and this is my functional space, which is bundle on it. You have functional on the whole thing, where you know what critical points are, they correspond, they eigenfunctions, you know everything about Morse index, and another functional is here. And so essentially the main work is to compare what happens. You know that the functional, at this point the functional on the big thing can have completely different Morse index than that one. So you need to be able to move from along fibers somehow to relate those critical points and their Morse indices. And this can be done. I cannot get into details. It takes some time to do this, but it's doable. And the result is that you connect this big space, which is our functional space where the relay ratio lives, and this base of this bundle where partitions live. And then you can actually prove this equality. Yeah, that's what I already said. And I have just a few comments to finish this. I already mentioned that you don't need to look at equipartitions. The same result holds if you look at the space of all partitions, not necessarily equipartitions. It's a bigger manifold, but the functional becomes non-smooth, but you can still interpret and formulate the same result. Now, what is bad about this? Morse indices, they tell you that there is some Morse theory going on there. And we know in Morse theory is not about one critical point. The nicest things are when you know the whole manifold. And you can tell something global about topology of the manifold through those critical points and the indices and vice versa. But we cannot do this, since when we assume generic partitions, what we did, this space of partitions is not a smooth manifold. It's something like this. We only know what happens here, what happens here. And those guys are disconnected. In order to cross this border singularity, we need to allow the nodal lines to collide. And we didn't do this. So what should happen, as in finite dimensional Morse theory, it's something like analytic variety. So it's not smooth everywhere, but it can be stratified. This is a smooth piece. And this is a smooth piece of higher codimension. Inside of it, there will be smooth pieces in even bigger codimension. And in this case, we are in infinite dimension. It can go far. And so, in principle, there exists what is called stratified Morse theory, but we haven't done this thing. It looked very scary. And I didn't do this, but right preparing for this talk, I understood that probably one can do something there. But at least without allowing partitions when they cross, you cannot use much this information.
I actually have a question, because when we discuss critical points on the set of these, how you call them,
Equipartitions.
equipartitions.
Generic equipartitions.
Yeah, equipartitions. How do you control that critical point itself will be in this set and does not go to the boundary of this set?
I don't claim anything about this. The claim is that all critical points are in one-to-one correspondence with nodal partitions. That's all. For instance, if I'm sitting in the piece, you're right that I cannot control it. There will be critical points on those singular allocations as well. And that's what we didn't do. But for instance, it can happen that I'm looking for partitions that has, I don't know, 5 pieces. Maybe there is no eigenfunctions that has this nodal numbers, and I will not find any critical point there. But you are right that since genericity condition, equipartition is not a big deal. Our genericity means that I throw away all singularities of this enormous space. And probably something can be done. I just started thinking, I don't suspect I know how, but still, I don't know what will be the result. The interesting thing was done by Gregory Birkalaika for graph case, and when Calandre-Verdier learned about this result, he provided a different proof. Calandre-Verdier thinks it's better proof. I think Birkalaika is simpler, but it doesn't matter. They published in the same issue of Analysis and PDEs. You see, here we have to perturb partitions. This is something enormous. What they did in graph case, what Birkalaika did, Calandre only reproved this differently. He showed that instead of perturbing the partition, what you can do, you can perturb the operator adding a small magnetic potential. Small magnetic potential. If you add potential, you cannot discuss magnetic potentials. There are no nodal sets anymore because the function, the eigenfunction is not real. But the eigenvalue will still get perturbed. And if you look at eigenvalue as a function of those small magnetic perturbations, this is finite dimensional perturbation and much more physical. You perturb by magnetic potential. Then they proved that the Morse index of this eigenvalue with respect to magnetic perturbation also is related to nodal partitions, but in a different way. This new Morse index, let's call it M. M. It is number of zeros minus n minus 1. It's equal. This is on the tree you would have this equal to 0. But if the graph has cycles, you might have more zeros than n is the number of vertices. So, no, n is a number in the spectrum. And so you take this surplus of zeros, and it happens to be Morse index of the eigenvalue as function of small magnetic potential.
So this is when the magnetic potential is vanishing, right? You take the limit.
Yes.
So he does the variation, he studies
Yes.
the variation with respect to this magnetic potential.
Yes, you have no magnetic potential, but then you add eigenvalue starts moving analytically, and the Morse index is this. It is much more interesting thing, and we have never figured out how to do this for billiards. It looks like for billiards it would require you to subtract 2 infinities to get some finite answer, which also suggests that maybe there is some phenomenon algebra with trace there, but I don't know. That's all.
Okay, thank you. Are there more questions or comments? Please do.
Is it known whether you could have finite lim-inf of nu n and simple spectrum?
I think so. I think so. As an actual question, since so the Stern example uses multiplicity.
Yeah, exactly.
But I think even with I am practically sure that even with simple spectrum, it can happen.
And even true, for example.
I don't remember exactly.
But when you say you're almost certain, it means almost certain such examples are known.
Yeah, I think that I know, but I wouldn't be able to right now produce one.
But you can take the torus for the Stern example, and then you look at a block vector with the irrational k. You have simple spectrum, and you can probably still do the same perturbation. Eigenfunctions
No,
are complex.
What Leonidas
No, maybe
is
not,
an example like Stern when you have very
Yeah.
low number of nodal domains. I don't know whether you can.
No, okay, so make it irrational, instead of square.
But then it cannot be a nodal set of eigenfunctions, since eigenfunction, it will force eigenfunction to be equal to 0.
Then all
No, I mean-
eigenfunctions would be sort of sign
Would still be,
axis.
right?
Sorry?
Then you perturb.
But I cannot perturb. Or perturb by what? By
Well, the Stern example.
for
was a
example,
square.
it's just a square, yes.
Yeah, and then why not do the Stern example on a rectangle to break up the multiplicity?
Yeah, but then the Stern example, I mean, Stern
Yeah,
example.
but
then
then,
you use
but then
it.
still you need to know that there is such example. I think that it is known, but I don't remember exactly.
Comments or questions? Well, if not, thanks very much, Peter. And we have a 5-minute recess and start at 3:10 again.